In this lecture, we will consider the basic concept of radioactivity and radiation. Radiation safety is a set of measures when working with the use of radioactive substance and other source of ionizing radiation, ensuring a reduction in the total dose of all types of ionizing radiation. Ionizing radiation is the radiation, the interaction of which with the environment leads to the formation of ions of different signs. Ionizing radiation, which is composed of charged particles such as electrons, protons, alpha particles, which have sufficient kinetic energy to ionize upon collision, is called directly ionizing radiation. Ionizing radiation, which is composed of uncharged particles such as neutrons or protons, which in turn can create directly ionizing radiation and cause nuclear transformation, is called indirectly ionizing radiation. Photon ionizing radiation includes gamma radiation, which occurs when the energy state of atomic nuclear changes Brem strength length with a continuous energy spectrum, which occurs when the kinetic energy of charged particles decreases. Characteristic radiation with a discrete energy spectrum, which occurs when the energy state of the electrons of an atom change, and X-rays consisting of Bremsstrahlung length and characteristic radiation. Corpuscular radiation includes alpha radiation, electron, proton, neutron, and meson radiation. Radioactivity is understood as the spontaneous transformation of an unstable nuclide into another nuclide accompanied by the emissions of ionizing radiation. A nuclide is a kind of atoms of one element with a given number of protons and neutrons in the nucleus. A nuclide that is radioactive is called a radionuclide. The distribution of ionizing radiation in the medium under consideration is called the field of ionizing radiation. Field of ionizing particles, flux density, observed dose rate, Kerma rate, etc. Radionuclide activity in the source sample A is the ratio of the number of spontaneous nuclear transformations occurring in the source or sample over a time interval to this interval. The unit of activity of radionuclides is Becquerel. Becquerel is equal to the activity of the radionuclide in the source, in which one spontaneous nuclear transformation occurs during 1 second. The off-system unit of activity is Curie. Curie is the activity of a radionuclide in a source or sample, in which 3.7 and 10 in 10 11 spontaneous nuclear transformation occur during 1 second. Spontaneous nuclear transformation is called radioactive decay. Radioactive isotope nuclei are unstable. They spontaneously disintegrate and form the nuclei of new elements. At every second, only a certain fraction of the total number of atomic nuclei of a given radioactive element decays. This fraction, characterizing the probability of decay, is called the decay constant or the rate of radioactive decay and is denoted by lambda. The rate of radioactive decay is constant for each given isotope and does not depend on physical and chemical conditions. It is associated with the average lifespan of radionuclide, T equal to this formula, where T is the time required for the complete decomposition of any amount of a radioisotope at a constant decay rate. Spontaneous decay of radioactive nuclei occurs according to the law of radioactive decay, whereas the number of nuclei that decay in a short period of time and is the number of active nuclei available at a given time. To characterize the decay rate, it is customary to use the value of the half-life or time during which half of the original number of atoms undergoes radioactive decay. There is a relationship between the half-life and the decay constant lambda expressed by the following equation. For various radioactive isotopes, the half-life varies widely. Chains of radioactive decay of radioactive series, the ancestors of which are radionuclides, have significant stability and a long half-life. They are called radioactive families. There are 4 radioactive families. The ancestor of the first is uranium, second thorium, third actinium, fourth neptunium. The longest lived uranium 238 has a half-life of almost 4.5 billion years, and polonium 214 is less than a second. To determine the harmful effects of radionuclide after the later enters the human body, the so-called biological half-life is established, during which half of the observed radioactive isotope will leave the body. Using the biological half-life of T biological and the physical half-life of T physics, it is possible to calculate the average effective period of exposure to radiation on an organism or any organ. The effect characterizes the time interval during which the body tissues were exposed to radiation due to the decay of the observed radionuclides. In the table shows the values of T physics, T biological, and T effective to some radionuclides. As can be seen from the table, for carbon-14, the physical half-life is more than 5,000 years, while the effective and biological half-life is only 35 days. Measuring the nucleate content in ancient organic remains, skeletons, mummies, wooden objects, and etc., all is archaeological to determine the age of these objects. Saying this lesson is over. Thank you for your attention.